could be in two places at once. That their fates are dictated by chance. And that reality itself defies all common sense. Could be in two places at once. That their fates are dictated by chance. And that reality itself defies all common sense. And at stake, that everything we thought we knew about the world might turn out to be completely wrong. The fruit fly experiment gives hard evidence that quantum smell theory really works. Incredible as it seems, flies, humans and dogs may be smelling the sound of quantum biology. Our sense of smell is fascinating and mysterious as it is, but to think that when I encounter a particular scent and that sets off a whole wave of memories and emotions in my mind, that it's underpinned, that it's triggered by quantum mechanics, I think makes it even more remarkable. The mysterious influence of quantum physics reaches into every corner of the natural world. In fact, it inhabits the walls of every living cell on Earth. Because the latest experiments suggest a magical solution to one of the greatest mysteries of nature. The miracle of metamorphosis. The transformation of a tadpole into a frog has never been fully explained. In little more than 6 weeks, the tadpole breaks down, then reassembles in its adult form. But the big mystery is how it happens so fast.
Nobel Prize-winning researchers in physics have proved that the universe does not physically exist in a single place. Currently, quantum informatics is among the most active directions in the field of physics. It brings together Einstein's general theory of relativity and quantum mechanics through the still mysterious behavior of black holes. It also deals with the construction and operation of quantum sensors, which are increasingly being used to study everything from earthquakes to dark matter. It also often elucidates the perplexing nature of quantum entanglement, a phenomenon that is essential to modern materials science and underlies quantum computing. What makes a computer a quantum one? Nicole Younger-Halpern, a physicist at the National Institute of Standards and Technology, asks rhetorically, one of the most common answers is entanglement. And the main reason we understand entanglement is because of the tremendous contributions of Bell and 3 2022 Nobel Prize winners. Without understanding entanglement, quantum computers probably wouldn't have been created. Complex experiments with entangled light have revealed a profound mystery underlying reality. One of the most disturbing discoveries of the last 50 years is that the universe is not locally real. The term real means that objects have rigid properties that are not affected by observation. That is, the red apple can remain so even when no one is looking at it. Local means that this apple can only be affected by its immediate surroundings, and any measurable influence or causes, according to the normal rules of physics, cannot travel faster than the speed of light. Research at the limits of quantum physics has shown that these two things cannot be true at the same time. It shows that objects are not only affected by their environment, but also that they may not have certain properties before they are measured, which of course is deeply at odds with our everyday experience. As Albert Einstein once said to a friend, "Do you really think the moon isn't there when you're not looking at it?" A phrase from the writer Douglas Adams shared that the rejection of local realism made many people angry and was generally considered a bad move. And the three scholars, John Clauser, Alain Aspect, and Anton Zeilinger, get the blame for it. In 2022, they jointly take the Nobel Prize in Physics for experiments with tangled protons, demonstrating the violation of Bell's inequalities, and pioneering the science of quantum information. This award was highly anticipated by their colleagues, who said it was an extremely well-deserved recognition for upending reality as we know it. From the 1940s until recently, research on quantum fundamentals was often dismissed as a philosophy or even nonsense. Many scientific journals refused to publish articles on the subject, and academic positions that allowed for this kind of research were almost impossible to fill. In 1985, Sandu Popescu's mentor warned him against doing a PhD on the subject, telling him, "If you do, you'll have fun for 5 years, and then you'll be out of a job." Nowadays, quantum informatics is among the most dynamic subfields in all of physics. Among other things, it clarifies the often confusing nature of quantum entanglement, which is an essential element of modern materials science and underlies quantum computing. The main problem with quantum mechanics has never been its accuracy, since it worked great from the beginning when physicists developed it in the early 1900s. What Einstein, Boris Podolsky, and Nathan Rosen had a problem with was the influence of the theory on reality. Their analysis, called EPR, is based on an imaginary experiment to show how quantum mechanics can break down under certain conditions and defy our beliefs about reality. The Nobel Prize-winning experiments showed, however, that two particles, regardless of the distance between them, can remain entangled in the quantum realm. This contradicts local realism and Einstein's theory of relativity. In theory, two particles could be at different ends of the observable universe and still be entangled, a concept known as non-locality. Alain Aspect, John Clauser, and Anton Zeilinger conducted groundbreaking experiments using entangled quantum states in which two particles behave as a single entity, even when separated, the Nobel Prize review said. Their results cleared the way for new technologies based on quantum information. The 2022 Nobel Prize in Physics was actually awarded for an experiment dating back to 1972, and numerous subsequent ones that showed that the local realism view of the universe was wrong. It clarified what quantum mechanics really means, said Professor Thors Hans Hansen, a member of the Nobel Prize Committee for Physics, in connection with the award. The scientists' findings actually show that the universe cannot be locally real, because particles do not have certain properties of spinning up or down before they are observed or measured. Therefore, the simple act of observing a particle changes its state, which contradicts the rules of local realism. In other words, the universe is real, but only when we observe it. Experiments, starting with Clauser's earliest and continuing onward, show that these conclusions are not just philosophical, but real, and like other real things, potentially useful, says Charles Bennett. What does it all mean? Quantum physics claims that the universe is random, and that the state of particles, such as electrons or protons, can only be predicted using a probability distribution due to their non-deterministic nature. In other words, we can predict how particles will behave once they are observed only within a given probability. The theoretical probability distribution is called a wave function, which contains information such as the position and momentum of the particle. Here, however, it gets even more complicated. The very fact of measuring or observing the particle collapses that wave function into a given state of the particle, which we can then observe, a phenomenon known as particle-wave duality. In the theory, this is what makes the universe random. But scientists still don't understand why and how the wave function collapses. This collapse is called the problem of measurement. So what, for example, does the particle look like before it is observed? We cannot know, because before the observation, the particle is in a state of quantum superposition. This means that it is in infinitely many different states at the same time. You're probably totally confused by now. Don't worry, because in the end, all you need to know is that at the quantum level, nothing is as it seems, and that the discoveries of John Clauser, Anton Zeilinger, and Alain Aspect shook the world of science, turning reality on its head. The growing investments in quantum technology now being made around the world are based on scientific foundations that stem from the pioneering work of Bell, Clauser, Aspect, and Zeilinger, said John Preskill, lead scientist in quantum information at Caltech Institute before Scientific American. Share your thoughts on the topic in a comment. Support us by subscribing to the channel and sharing this video.